No, I didn't know the car was, you know.
Okay,
Oh, I don't know about it.
almost time to get started. Anyone have any questions about anything before we get the ball rolling on a good chunk of the rest of J unit?
Did you see my email?
Yes, yep, I've gotten a couple emails. I need to actually check the contents of those to make sure that the tail recursion is implemented correctly, but haven't had a chance to do that.
Yeah, I'm surprised.
I was in office for office hours or teaching between 9 and 3:30 yesterday, so I got no prep done. It was just a day of answering lots of questions, which is good. I appreciate when students come by and do that, but in a quarter where I have to make all of the content for both classes, there's work that needs to get done. All right, it's basically time to get started. We should do that. Remember, for those of you joining remotely, that I can see the chat. So if you have any questions or want any clarifications, post. I might not see it immediately if I'm at my laptop or doing anything to the screen, writing on the board, but I will be occasionally checking chat. So please feel free to leave any clarifying questions or any answers to any questions that you have that I post to the class in chat. I'll check that. Okay, today we're talking about the rest of the JUnit assertion methods and then continuing on with more JUnit stuff. So last time we talked about how there are lots of built-in assert methods into JUnit. You can do things like assert true, which is going to check the test in the parentheses there. If that test evaluates to true, then the test will succeed. Otherwise, the test will fail. Assert false is exactly the opposite. It will run the test and it will succeed if the result of that test is false and will fail if the result of that test is true. So you're expecting the value of that test to be false. If it is not false, then the test fails. So just negation, a little bit of double negative in there. You can also assert equals. So you pass it an expected value that is your own calculation of what the result should be. And then the actual will be some expression that calls your code to compare whether or not the expected value and the actual value are the same. So that will fail if these values aren't equal. Assert same checks if they're not the same by equals equals. So again, this is kind of the dot equals. This is the equals equals that we talked about before, where this is more of a shallow copy and this is more of a deep copy. So different logic for the same kind of equality checking. So you can do the same for assert not same. So this is just like assert false is the opposite of assert true. Assert not same is the opposite of assert same. So this fails if they're not the same, and this fails if they are the same. You can assert null, which will fail if the value is not null. So you'll use this to check whether or not you expect something to be null at a particular point in time. And we know, hopefully we've seen at some point throughout our coding education that dereferencing null leads to a null pointer exception. So this allows you to check that in a test case without actually dereferencing null. And I just want to make sure that that point is clear. Again, we talked about how we have variables that point at structures. And what happens if that structure is just not there? This is something like, what is at the third index of this particular structure? We can answer that question if there's a structure here. We cannot answer that question if there's not a structure here. What I like doing to make this a little bit clearer is this is a reference, and in other languages, you can kind of call this a pointer, the concept of dereferencing this and pointing at what's there. I could cold call someone in class, and if I'm pointing at an actual person, then that person would know that I was referring to them. But if I point at an empty chair and sit there waiting for an answer, I'm going to be waiting for a very long time. Java cuts that out and just says null pointer exception, and that's basically what that is. You're pointing at something that doesn't exist or is not there. So it doesn't know how to respond. It doesn't have the methods. Like this object has methods associated with it that are the expected behavior of that object. If the object is not there, and I say student sitting in that empty chair, jump, that can't do that. The absence of a student there cannot jump and do that associated behavior. So it's useful before you do something like dereference null, check if it's null first. And you can check if something is null at a particular point in your code by using an assertion test. So assert null or assert not null, making sure something is not null before you dereference it is a very good thing to do. So you may be at line 67 in your code and you're in the middle of a function. At some point, there should be some value for a particular structure. You should be able to dereference it. So you can assert not null and make sure that thing is actually instantiated in there. And that way, that will fail if during any of your test cases, you reach that point in your test and say, hey, I expect this to not be null. There's also this lovely fail function that no context just fails the test. There are some times where you reach an internal state with some logic where if this particular logic is true, then you want it to fail. And you can just display that logic, do something, and then if a particular conditional is met, just fail. So this gives you lots of logical opportunities to construct tests in the best way, the ways that make sense to you. There's a lot of equality. You can make the same test calling a bunch of these different functions. And similarly to how if I give you a problem, you all might solve it differently, but those solutions are all technically correct. You just use different logic to construct that. You can do exactly the same thing with tests. Tests are just more code. There's no one right way to construct a test, but there are better and worse ways to construct tests. And we'll spend the rest of this lecture talking about what good tests are and what bad tests are. All right, here's an example. This gives you an idea of what some of this test code might look like embedded within a program. So we have an array that is meant to store some integers. And some kind of, this is gonna be an array list, but the structure that we've made is an array int list. So it's not quite as generic as an array list. It's just meant to store integers. That's great, it has the same functionality. We make the list. So this we call test add get one. This is just gonna run this code and make sure this code does what we would expect it to do. Note that this is not necessarily tied to any, it's kind of like a driver class in that we're instantiating an object, we're filling it with values, and then we want to assert equals the value that we say that we added here with the value that's stored in position 0 in the array. And we can do the same thing where we expect -3 to be at position 1. We expect 15 to be at position 2. You would think that this test would never fail, right? You'd be surprised. There's code that you could write that would make this test fail. Here's another test. Test is empty. We're going to make an array list. We want to make sure that assert true. When you make the list, it's empty. Then you add a value to it. Then you should be able to assert false is empty. That should be true, right? It should no longer be false that it's empty. So if it is false, that it is not empty, then this assertion is true and the test would succeed. Kind of some double negatives in there. And then finally, remove the element at that 0th position, assert that it's empty again, and that should also pass. So this just makes sure that from an empty list, you can add something and it stops being empty, and then you can remove the one thing that you added and it remains empty. So this is a full test of this is empty method that you would write. So you can see how this tests the add method, this tests the is empty method. So you can map tests to particular small pieces of code, methods within a particular class, that you put some expected behavior in here, and then you can determine whether that expected behavior actually comes to pass or not. Questions about this example? Make sense? Intuitive? All right, let's say we finish this off. It just has these couple tests in it. We want to figure out how to run it. Within IntelliJ, this is again from within IntelliJ, and There will be a similar way to do this for different IDEs and different languages that you do something other than JUnit, but you should be able to do something pretty similarly to this. There's a hollow play button that you can do to run each particular function. So you can run an individual test like this. So it says, just run this particular test right now and see whether it succeeds or fails based on the existing code in your object class. If you want to run all of the tests, there's going to be a double hollow, and that will run all of your tests all at once. So again, saves a bunch of time.
Well, what's the difference from like JUnit 4 and 5?
I have not looked at the actual change log, but additional functionality, additional bug support, that's usually why they release a new version of JUnit. People are always looking at what additional functionality would be nice and trying to implement new things. But go look at the change log and let me know exactly what changed between 4 and 5, and we can talk about those. Good tests. So I see this a lot, and as I was talking to Stu in preparation for teaching this class, Stu is a serial pessimist. He always talks about students like they are, here are the pitfalls to avoid. And he gets frustrated when students program to the test. Basically, you're writing code so that the tests that I give you pass, not so that it implements the functionality that you're supposed to implement according to the API. So the first horrible rule that I do not want you to break is the goal of testing is not to write tests that pass. It's to write code that all of the similar kinds of tests would pass. The goal is to map to the functionality, not to the test, especially in this class, because there will be some tests that I will give you. I will just straight up give you some test classes that say, pair this with the code that you run and run the tests. All of those tests might pass. I will be using additional tests that are not given to you when I grade it. So if you program to the tests that you are given, you may fail some of the tests that I hold back. If you program to the functionality, then it should work regardless of the tests that are written. So the goal of testing actually is to write the tests that are most likely to fail and reveal issues with your code. If you're designing tests, you want to design the tests that are most likely to fail, which is kind of counterintuitive because you really want them to pass. But at the same time, what's more important than your test passing is your code doing what it's supposed to do. The tests are supposed to reveal yes or no, your code does what you think it's supposed to. So this means that you should think critically as you design tests. It's not just a come up with some tests. Hey, I designed 10 tests. That's great. I think I'm done. It's thinking about what are those tests that are most likely to fail. If you write a test and that test cannot fail, there's no point in the test. It doesn't tell you anything. It's never going to reveal a bug. Not all failure points are equally valuable. If you think about the ways that your program might terminate that might be really annoying to an end user, or in the absolute worst case, kill your end user. We talked about that last time. But you want to make sure that you have very high test coverage of all of the possible ways that your tests can fail in a fatally bad failure. And depending on what you design and code, that will look completely different. What those important failure points are going to be will require you to think about how people are going to be using your code. As you think about that, you'll figure out, I really don't want my code to fail in this way. A lot of your thinking and test planning time should go into preventing those kinds of bugs and testing for that kind of behavior. Failure points can also fail in different ways from different potential inputs. So just because you've written one test for a method does not mean that you have fully covered that method. So you may need to think about what test suite do I need to write to maximize the chances that this performs the way that I expect it does. A lot of features will need entire test suites, so you'll need lots and lots of tests. So here is an exercise for everyone to work on. I have a date class, and a date has a couple of different possible constructors. If you pass it the year, the month, and the day, it will set the current date to the date that you specify. If you pass it nothing, it will set it to today, whatever today happens to be. Then there are getters for get day, get month, and get year. There's a function for adding some number of days to the current date. So the current date is stored in the object. This just adds some number of days to that and returns it sets the date, the internal date object to be however many days have passed since then. There's a days in month that gets back the number of days in the current month. Day of week tells you the current day of the week. Equals tells you whether the object that is passed in is equivalent to this. So two separate date objects that store the same date. Is leap year will return yes or no as to whether or not the current year is a leap year. Next day advances to the next day, adds one day to the current day, and the toString will find some nice pretty way to print what date it is. So you would expect that today, for instance, would be January 17th, 2024. So what we care about, think about and design some unit tests. The unit tests should check the following abstract ideas. No date object can ever get into an invalid state. What is an example of an invalid state for a date object?
March 65th.
Yes, March 65th doesn't exist. What else? Yeah, so if we're storing the month as an integer, if we have, something like 15/15, and we're assuming that the first one is the month, then month should not be an integer above 12. Should also not be an integer below 1. We also don't, just like we don't want March 65th, we don't want March -4th. So what of these methods could potentially get a date object into an invalid state? And what do we need to check to make sure that something like add days is actually going to return a date object that makes sense? What kinds of tests would we need to write? Just think about that. This is a reasonably long exercise. I expect this to take a while. Think about it and try to write them out with those assertion methods from before. So you want to make sure that add days work properly and that no date object can ever get out of place. So we'll take something like, 5 to 8 minutes. I know there aren't too many people here, but find someone you can work with maybe. You can work in small groups on this, talk it out, plan it together, bounce ideas off of each other. Those at home, make up an imaginary friend and work with them.
Invalid state first, because we should make sure that can't get in before that. -200. Sort of thing. I guess, yeah. Yeah. Yeah, we just have to make sure that we can only enter a real date.
I'm quickly going to switch the slides back to the assertion methods so that you can also take note if you want to write down some of the assertion methods that you might need for this.
Should we just be like coming up with ideas right now, or should we actually be like writing down? jotting
I
down
would-
code?
I would write pseudocode if there needs to be pseudocode, but try to put the actual, figure out which assertion method you would use. And then pair that assertion method with some pseudocode logic to figure out, like, if you're doing assert equals, then some pseudocode for what the expected would be. And then the actual would probably just be a quick method call. Good questions. Does everyone have what they need from these assertion methods? Those at home can take a screenshot.
Do you have to import the J package?
Yes, if you're doing the actual coding. But I'm assuming that people will probably do this on paper. The only reason to do this digitally would really be if we had the date class so that we could run the date code. Because we don't even necessarily know how these are implemented, so we can't really call these functions until we implement them ourselves. And it would take a few class periods to implement the entire date object. All right, I'll switch back to the methods.
Some sort of catch.
Anyone have any questions I can answer? Yeah.
I was just say, does the program automatically know how many days are supposed to be in each month apart from February based on if it's a leap year or not? Or is that defined somewhere in the code?
You could assume that that logic is implemented. You should not need to implement any functionality. So yeah, all of these methods will do what you would expect them to do. All you have to do is write the tests to verify that what someone else implemented here is correct. That should involve no actual implementation on your part, just checking the existing implementation. Great question.
month there is the length. Oh.
Make sure the- all right.
It's relevant to do that for you. Because we have these checks. So,
So that. The date.
yeah, that only comes up.
Yeah, let's go over a few of these just to get a sense of what we might be looking for. We're gonna come back to this exercise as well after I talk about tests that are written in good forms versus bad forms. And how to write better looking tests that work better. But intuitively, let's just start thinking about, let's start with the add days method working properly. What kind of tests would we need to write for add days to make sure that it is functioning correctly? What parameters, what values should we pass it?
First one was 32.
32 seems like a reasonable value. Why 32? What would you expect that to do?
That's a day longer than.
The longest month, so you know that you're in a different month than you started with? Sure. What else could we pass it to test something else? What was that? Negative something? That seems reasonable. If you pass it a negative number, what would you expect it to do? Go backwards in time? So it's basically the equivalent of subtract days. You don't really need to subtract days if you have an add days with a negative number, but it's something we certainly want to test to make sure that the days roll back appropriately, the months roll back appropriately, the years roll back appropriately. What else should we test? Again, you have no idea how this is implemented.
Also, 1,000 days.
Yeah, 1,000 days, make sure you're in a different year. And again, the actual test construction for this, you'd be doing a lot of assert equals because you calculate what 1,000 days from today is. And you could create an object that has exactly that date and then assert equals that the object that you created from 1,000 days and the code where you pass add days 1,000 and check the current date, those should be the same. Those should be the same at a deep copy level. Make sure you're not using equals equals for that because they're technically separate objects. Because you would have something like some date object down here, some date object down here, and these date objects would store the same date. If you're checking at a shallow copy level that says, are these stored at the same place in memory? Are they the same object? They are not. That will fail, even though they have the same underlying date object or the same date object value. They're technically stored in different places. They're a copy of each other with the same value. So you need a deep copy level to make sure that they have the same values. Anything else we want to test? Can you imagine basically, whenever you finish writing a test suite, the question you can ask yourself is, could I possibly write code? Is it possible at all for me to write code that passes these tests and is still wrong in some capacity? If the answer is yes, what is the associated test that would fail where these succeed? Then think about that and design that test. So that can reveal holes in your testing logic or your test suite. Yeah, maybe we want to pass in, this is an integer, so we should probably do something like pass 0 and make sure it's the same date. Nothing happened. What happens, since this is a primitive int, are there any really weird values that primitive ints can take? Ints can't technically be null, only objects can be null. That is a good idea though. If this took an object, then you would want that. If this, for instance, was a wrapper class, instead of int, it had integer written there. That's the wrapper class for int. Have we seen those before? Seen wrapper classes? Know what those are?
Max value.
Yeah, you can check integer.max value. Although if you check integer.max value, what would you expect to happen? It should wrap over in some sense. If you add a bunch of days, add billions of days, and you're storing things like the year as an integer, then if the year ever got so high, it could wrap around from a really large positive number to a really large negative number. But if you added integer.max value days, you don't expect the year to quite get that high. So I would think that integer.max value would be a reasonable value to pass in here. But I'm going to take a quick aside and explain this concept of wrapper classes for those who haven't seen them before. So an int is a primitive that stores 32 bits and can be represented by some number like this. So it's just, it goes in a box. We could write the number 1, we could write the number -1, we could write anything up to and between -2 billion something and 2 billion and something. A wrapper class, if you type a capital I integer into this, what you're defining is an object where the main field is this integer, this int, this primitive int value. But there are also some other things. So you note that you can't do something like int.max value. You need capital I integer.max value. There's an additional field, static final field stored that is a representation of the maximum possible integer. And when you say integer.max value, it's just doing a lookup into this class to say what is the value of this static field that represents the largest possible integer that we can store. Same with integer.min value. Has anyone called something like integer.toString to get you back a string representation of an integer? That's a method. So we split classes into fields and methods. This has the logic that converts the integer into a string version of that integer. So you can add behavior to this as well of things, typical things you might want to be able to do to an integer. So if you have a wrapper class like this, it really is just a class with state and behavior. The state stores the actual value of the integer and any other static constants that you might care about, like the maximum value. And then the behavior is common functionality that you might want to do to an integer, like convert it to a string. These wrapper classes exist for every primitive type. So capital D double, capital F float, capital C character, they all add behavior to the primitive variable types that you have seen before. Questions on wrapper objects?
Primitives like a Java that are objects or still objects?
They are not objects. Yeah, they're just basic data types. All right, I think this is probably good for now. We will come back and do a much more thorough covering of these questions when we come back to it after talking about how to make tests well-formed. so that I don't go over some poor ways to do this and then come back and do some better ways to do this. I feel like that would waste some time. So here's an example of some errors in tests. So on the left, we have the code with the error. On the right, we have the code with the error fixed. So for this first example, what did they get wrong? Yeah, we have expected and actual. And expected and actual. So even though this is going to compare the two things and they're going to look the same, anyone who looks at this test is going to expect that the expected value is on the left and the actual value is on the right. So the expected value is going to tell us what we expect it to be, and the actual value should be what the code produces. If you flip them around, it gets confusing for someone reading the test. Again, it will not affect whether or not your test succeeds or fails. It's just test readability. What about this lower example? What's going on here?
He's like, that's just into the terminal.
Yeah, these print as you run the tests. So if this were to fail, if this test, you got a big red X next to this test, and this was the test you had written, how easy would it be for you to figure out what happened? You have to go back and reference the code, right? We don't like doing that as programmers. If we can get away with all the information you need to be able to debug what happened, if that's printed to the terminal, that's great. You don't have to go back and look at the code until after you understand what happened. If the test fails and you don't even know what the test did, that's bad. You have to go back and isolate and try to figure out, okay, which test failed? Okay, I guess it was this one. All right. What is this test doing? It's adding days. Okay, so if I take a year and you're going back to the code and having to logic this. Whereas if you see year after plus 14 days, month after plus 14 days, then these have some message explaining what is being checked. And when it fails, you get more information faster. This is especially true if you have different people writing the code and writing the test. If you didn't write the code and you wrote the test, you want to be able to read the test and communicate the failure back to the person who wrote the code. And just being able to copy and paste the error messages, if you have good error messages, that's fast communication. You'll be really fast at your job and really efficient. If you do this, then you have to create an error report to send to that person about what didn't work. So if you embed it in the message, it's just faster. Questions about either of these clarification types of errors in tests?
So we,
Yeah.
so it, the straight is expected is actually the answer you're expecting to have. So for
Yeah.
example, like if you say 1 + 1 = 2, 2 will be expected and your program will be on the right hand side.
Yes.
Okay.
Yeah. Good clarification. We want to structure our test code to be readable because again, you might not be the only person interfacing with it or who knows how much time is going to elapse between when you wrote this test and when it's going to fail for the first time. It may fail for the first time 5 years from now after some programmer who doesn't even work for the company today goes and makes some change that breaks your test. If that's the case, you may not even be working there anymore. Or if you are, you don't want to field questions from this brand new programmer about why that test was written the way that it was or why it failed. If you can structure your code to be readable, people won't bother you with questions that could have been avoided. You won't have to go back and refer to the test that you wrote to figure out why it failed. So front-loading the time and effort into well-designed code and well-designed tests will save you a ton of time when you write larger programs. Again, if you're just writing a very quick Project Euler first couple problems like we've done in class so far, you do not need this level of coverage. The program is not meant to live past getting you an answer. It's not something that you're going to need to expand or maintain over the course of months or years. This is all for the larger kinds of programs you will be writing. So stuff we're going to show here will improve any prior test code to make it more readable. So here are some examples from the prior example. So we can now call something actual and call something expected. So now when we do the assert equals, we have a variable called expected. We could easily put all of this code inside of this assert equals and make it look really ugly. The more you can phrase your code in terms of what it actually is. So this expected tells you what the expected data is supposed to be. Very straightforward, very readable. This is the expected, this is the actual. You don't even need to refer to what comes first, the expected or the actual. Because you have a variable right there called expected that tells you the order. The person who wrote this test obviously took a little bit of time and effort for the clarity of their test. What happened down here? We have expected, and then we have our nice print together. That's great. Much more readable. Questions on this? The next thing we want to talk about is how do you name your tests? Think of this like naming a variable or like naming a method. It's very important what you choose that name to be. Did anyone start programming with variables like A and B and C and quickly realize how difficult that became after your program expanded beyond 3 or 4 variables? I started that way. I was a silly undergraduate when I took my first programming class and did a lot of things that knowledge makes you regret. It's one of those things that you don't see the value of until it's a massive problem. It's the same thing with tests. You don't want to name them arbitrarily. You want to name them something that helps you understand what the test does. So your name should tell you as much about what it is testing as possible. You get information directly from the test failure message. It will tell you the name of the test that failed. If that name is a good name, you will know immediately what happened. If you name your test some random string from just mashing the keyboard, you'll have no idea what failed or why. Those are just the extremes. So here we go. Test, add days, underscore, within same month, underscore 1. Add days, underscore, wrap to next month, underscore 2. These are very descriptive names that tell you exactly what the test is testing for. And then the test is the code that gets you that logic. When it fails, if you see add days within same month, and then it tells you date after plus 4 days, you know just from that adding 4 days without wrapping the month over failed for some reason. And you can immediately go start thinking about why did that happen?
Will it tell you it's even use?
Yeah. So it will tell you the expected and it will tell you the actual. Bam, right there, you'll be able to compare and see why is this expected different from this actual? How much is it different by? What in your code might have caused that difference? So this allows you to immediately apply logic and critical thinking to your code from a test that you wrote. And also note that as you write this, could you write this test without the actual code? Implement it yet? Does the code need to be implemented to write the test? No. You need it to run the test, but you can start planning the functionality of your program by writing the tests for it. And then you write the code and see if your code maps to the tests that you've already written. That can be extremely useful. We call that test-driven development. I think I've mentioned that already, but that concept will keep coming up. And Maybe I'll even provide some statistics for you to see how much time this can save on average. Not everyone buys into it, especially those who don't believe in tests. But the reliability of your system can get a massive increase from writing more tests. All right, good assertion messages. So how should you word your assertion messages? So in the output, answer to that question tells you the expected and actual values. So you do not need to include them in your actual test output. You do not need to include expected was this, actual was this. You will see that in the error message when your test fails. Here's the bad. Let's see if we can turn the bad into the good. Take a look at this test and tell me what could be improved here.
I could probably get rid of all the text.
There's a lot of text here, right? We're gonna see expected here and here. We're gonna see actual here and here. So,
That's gonna display regardless of whether it fails.
yeah,
Right?
yes, and then it also displays regardless of whether it succeeds or fails. So here's a much better, you describe what you did and then get the expected and the actual. And this only prints if the test fails. So everything will just get green check mark with no information. And as soon as you get a red X saying this particular test failed, you see the assert message. You have a loop in your code. That loop may run infinitely. And you would like to write some test that says, this loop should not run infinitely. The easy way to do it is set a timer and fail your test if the timer reaches 0. So that says this loop should have terminated by the time that this much time has elapsed. Timeouts are going to be, we'll give you an example of this in a second. They're static constants. So you can remove them from individual tests and refer to the same value for all of your tests. So you could have one, you can even have a short timer and a long timer. Your short timer is 1 second, your long timer is 10 seconds. Something like this. But you can factor that out of your tests so that it's in one place that you just refer to for all of your tests. And that way you're not making variable after variable after variable inside each of your tests. So again, we have a bad and a good. The bad does this. And this is the appropriate syntax, by the way. You, in your at test, in parentheses, you'll put the timeout equals the number of milliseconds. So 5,000 milliseconds is 5 seconds. The good is going to be to factor them out. Private static final int timeout equals, in this case, 2 seconds. And now, instead of hard coding this value at a particular value, you can set it to be an appropriate timeout. And this allows you, if you have multiple different timeout values, you can immediately see this is the short timeout or the long timeout. Or you could even have different tests for the short timeout and the long timeout. And that way you can see if it fails between the short timeout and the long timeout. You get the whole suite of options for trying to figure out, is your code performing the way that you would expect it to? Question about the concept of a timeout? Now that you know it exists, put it in every test that you write. All of your tests should succeed or fail within a certain amount of time. You can decide how long that is. If for some reason your test does not complete by a certain amount of time, rather than just assuming the test didn't finish or have when you run all of your tests, have that hang, your timeout will make sure that your test fails. And that way, if something really inefficient happens, or if you find yourself in an infinite loop for some reason, then your test will fail and notify you that because of the timeout is the reason that it failed. And that tells you a lot about what might be wrong with your code.
That's everything you have to do to make it work.
Yep. It's not a lot of work, so it should be embedded in every single one of your tests that you ever write. Just because it could fail for that reason, and it's good to know if that ever happens. We are basically out of time. we're just a little bit past the halfway point, so I assume we're gonna be lecturing tomorrow about this. And I like Fridays as just kind of problem solving days, so I'll probably try to get through everything tomorrow. Question?
Yeah, what happens, let's say you have like an infinite loop for like creating objects, right? You know the memory is gonna be outreach. Can you just do, instead of doing the timeout, be like size of this object cannot be equal to this many infinite amount of memory?
Not something as easy as a timeout, but you could specify that. There's a size of, just like there is in C++, where you can check the size of an object, so you could embed that inside of a test to check the size of your objects. And then set a threshold for that and then fail for other reasons. That is a good question. Any other questions before we disperse? All right, we'll see you tomorrow for some more tests. Thanks, everyone.
No.